Okay, so let's start again with these aperture antennas, in particular the horn antennas. Okay, so when we see in these cases that the general idea of this horn and open waveguide antennas are these metallic walls that we have in these cases. So they're covered by a metallic wall, and that means that the radiation cannot go out through this structure except through this open aperture that we have here. And we have a vanishing tangential component of the electric field that is inside of this metallic structure, on the metallic structure. We know that the tangential field has to vanish. And that's why we can have an electric field in these cases that comes, for example, in these directions here, because then you can see that the tangential component, they vanish on the top there because it's perpendicular. There's only a normal component to it. And outside here, the electric field vanish because it goes to zero. So the amplitude goes to zero. And that gives us the lowest solution of it. And then you can just think about the Fourier series where you expand the solution in sine and cosine function. So this is the lowest like trigonometric type function that fits inside of this structure when I have the condition that the tangential component of the electric field vanish. And that means, of course, that on this side of the structure and this side of the structure, you actually have this tapering. So there the amplitude goes to zero. And that means that side lobes in this direction and these directions are really low. Because there you have a tapering, zero amplitude, it goes up when you hit it, but it goes smoothly up and then it goes smoothly down and zero. When you look at the opposite direction, so the side lobe in this direction and at this direction, so the two different cuts of the side lobes, now I'm talking about the radiation direction, there you have high side lobe levels because the electric field is then high in the aperture and it goes to zero directly at the edge of it. Or it's you're jumping down to zero because what you say, the field is zero outside of the structure or close to zero outside of the structure. And that gives you high side lobe level. And that exists, of course, exactly the same there and there, this direction, high side lobes. In this direction of these cuts, low side lobes. And yes, the first propagating mode was this cosine shaped in some ways. And the only thing what happens with the horn, at least if you have a well-designed horn, it starts to come complications inside of it. But the first approximation, what you do is that you take this solution here and you basically make it larger. There are other effects that comes in because of course the propagation distance is now different from the center of this one to the center as it is from the edge to edge. It's further, so the phase starts to change over it. There are reflections. There is all kind of things happening. FECO or simulator takes care of it, but from the first approximation you can just think that okay, it's approximately the first mode, but it looks larger in some ways. And that means that it's larger, it's a larger aperture that radiates, which means you increase the, the directivity, you decrease the bandwidth of the structure. So you get a bigger aperture to radiate. That's the basic idea of this horn antenna. So if we look at an example here to understand what is the center frequency of the structure. So if we take a typical structure that we have here, we can look at the horn antenna where we say we have some dimensions, A1, B1, 6 centimeters, 3 centimeters in this case. And then we have the structure behind, which is the waveguide structure with some length C. And then we have some structures A and B in these ones. And you get the question to estimate the center frequency of the horn antenna. So what is the center frequency of this horn antenna? Then, of course, we have to start assuming things or looking at things, and that is that it's designed to radiate at its first mode. So we have to look at the propagating mode in the waveguide, which means that in these cases, this one and this one doesn't really matter at all. The length doesn't matter. It's only the structure of the waveguide. And the only thing that comes in there is the largest dimension of it, which is then A in these cases. So that is 2 centimeters. So then we start asking, what kind of modes can you start propagating inside of this structure when it is, for example, 2 centimeters long? For the second mode, B starts to come in. So that come in when the next mode can come in. That either depends if it's A or B. And in this case, when it's 2 times of it, they will come in at the same time, actually. And then we can get the first wavelengths. Yeah, that is when it's 2 times that one. So again, that is your half wavelengths. It's not operating at that half wavelengths, but it's not propagating at that half wavelengths. And you will get the second one, which is the double to that one. So the wavelengths is then half of that one. So 4 centimeters and 2 centimeters, which would give some center wavelengths if we do it in center wavelengths of approximately 3 centimeters, which would say that you have a center frequency of approximately 10 gigahertz. Because of course, you know 1 gigahertz, 3 decimeters, 10 gigahertz, 3 centimeters. That's a very simple calculation which you should basically have in your head. And if you would do it in frequencies from the cutoff frequencies, yeah, you get something similar. You will get 11 gigahertz. And the difference now comes in of the center frequencies, that the center wavelengths can be different from the center frequencies and so on. So you have to see that it is the one that looks between, but it's a little bit different when you do it in wavelengths and frequencies. But the difference is rather small. So what this means is that you can actually take a look at your structures and in some ways figure out where are the frequency range of these ones. So we will soon look at one horn antenna that looks like this. Okay, now it's not so simple, but it's round. But from these different shapes, you can actually know at what frequency it's operating. You just have to look at their dimension. And in these cases, yeah, take the 2 in the waveguide. Typically the longest one, when it's half a wavelength, it can start operating. It will be slightly higher frequencies that's needed. And it comes in when does the next mode comes in. And that is when that is 2 wavelengths. Or alternatively, it starts propagating half a wavelengths in the other dimension. And that range between there would determine the operating frequency band of this waveguide structure, which then translates to the operating frequency typically for the horn. And then maybe it's slightly below this due to some other constraints. And so very, very simple approaches for these cases. Then you can make slightly different horns, because as you realize now that when you make the aperture larger, you basically make a more narrow beam width. But then you can say, let's only make it narrow in one dimension. And if you do that, you get these sectorial horns. So you can take your aperture structure here again. You know, radiation from that is very wide beam. And then let's say I only wanted to make it narrow in some ways this cut that sits there. So if you do that, you will get a narrow beam in one dimension, but very wide in the other one. So here you will get a beam that in this dimension is very wide, but it's very narrow in some ways in these dimensions. Now it's hard to see my 3D cut. I try to draw over it. But when you go in some ways of dimensions in height of these ones, it's very narrow, but it's very wide in that dimension. And that's due to that this structure here, they then be much larger than lambda. And this one will be approximately lambda. And that means that if you take a cut along this dimension, it's very wide because the aperture is very narrow. And if you take the cut in this direction, it's the opposite that sits there, because then it's very long in wavelengths along that line. And that means that the beam width will be very narrow. And of course, you can do it in the opposite side. And then you get to the opposite structure. So here, in some ways, you get, when you take a cut in that dimension, horizontal in this case, it gets very directive, but it's very wide in height instead. And those are called sectorial horns in these cases. The CAN antenna I showed you. So this is the one. You can see it on the photo. You can see it here. It is actually the same CAN antenna that sits there. And this is one of the most, I would say, popular and simple to build, like Wi-Fi type antenna, if you want to build something at home which has some specific properties. And there are very simple design rules for it. You can find them on the internet, you can download them. And what the design actually goes down to in these cases is that you take and design your CAN. And in the CAN here, you have some diameter. and you have in some ways a feed that sits inside of it. Let me focus on the feed first. You can see it down there. There you can see the feed. And from the feed to the ground plane, there is some certain distance. And as I mentioned, there is a diameter. The diameter of this can should be large enough so there is a propagating mode. Now it's not exactly as simple as it was in the rectangular case where you can do Fourier expansion. Now you have to do Fourier expansion in the cylindrical coordinate. But that can be done. We don't do it in this course. Just. And then you have a distance here to the ground plane. And what should the distance to the ground plane be for constructive interference? Quarter of a wavelength. And now it's quarter of a wavelength inside of this waveguide structure, which is different from the free space one. But those are basically the design rules. So then to design this kind of antenna, you can go to your favorite supermarket. If you're here at LTH now, you can go to ICA Tuna. You can build a can of soup or something that you need to eat. Then you can drill a hole. You can put your connector inside of it. You put your little half-little stub that sticks up, which is the center of your coaxial cable. You make sure that the distance here is quarter of a wavelength in the can, and you have a good antenna. Very good practical. You can hold it with your hand here. Fairly good radiating out here. And of course, this is now an open waveguide structure, so the beam is quite wide, but it's a quite nice beam. It's very, very simple to build a Wi-Fi antenna. So yeah, as I mentioned, find your coffee soup, whatever, add your SMA connector to it, and the design rules again. Cutoff frequency from the cylinder here, so the diameter of the cylinder. And then you should have quarter of a wavelength from the back of it, where WG now is the wavelength in the cylinder. So you have to calculate what is that, and that's a different formula than the free space one, unfortunately. So they start changing there, but they can be derived, and there are very examples, for example, on the internet that says, how do you design your own antenna? Very, very popular antenna for these cases. And yeah, very similar to the rectangular case, but I would say more technical, so we don't do them here. This is an example. In the class, I usually bring this with me to show you. This is a photo from MIT installed of a system which called Build It Yourself radar system. You can check it here on this link that sits there, which is in some ways that you let students build their own radar system. That means you have to build your antennas, you have to build some of the electronics that sits behind it, you have to do some of the algorithms, and then of course you can go out and you can measure it, and you can do some imaging of what you see by radar processing of this to actually get, for example, the speed of a car or a bus driving by, or you can do some ranging where you see how far is it to some object. And we ran it here at the department, and you typically build this for $200 to $300 in some ways. Today you can buy a full radar system cheaper, but by building it yourself you learn quite a lot, and it looks quite neat. Now I cannot bring it since we're online in these cases. So that was typical horn antennas. And the first horn I showed on the first picture is what's called a broadband horn. So you can see it looks slightly different from this cartoon picture I had before with this typical standard gain horn more. It's very similar to what we have here. So you can see some ridges that sits here. This is dual polarized, that's why the ridge is there and there. The one here is single polarized. So you can see it's only this inner part in one dimension. And this broadband horn here, in this case, is designed for approximately 4.5 gigahertz to 50 gigahertz. So very, very wide frequency band. So much higher than this standard gain horn with one waveguide that just feeds it. And the difference in this broadband horn is due to these ridges here. So you can see the tapering of these ones. And when you do this tapering in the inside of it, you don't have to excite only one waveguide mode that then attached to something. You have this actually continuously going out. So the lower frequencies here is more related to the total size, or what to say, the longer wavelengths, lower frequencies, that's basically the total size of it. And the higher one has actually to do more with the feed inside of that one and the structures of that one. So for example, the width of these ones and the inner details in the feed. But you can get very, very broadband type of antennas coming out in these cases. You need a gradual transition in there. And what's happening here then is that the performance over this one, over the bandwidth, is changing. So typically here the directivity increases with the used aperture area. And that meant that how many wavelengths is this? So the structure here is like something like A lambda or N lambda or something. And the larger that is in wavelengths, the higher directivity you get of this antenna. So of course, when you are sitting at the lower frequencies, yeah, then this structure here is maybe lambda, which means the directivity is very low. And then you go up to 50 gigahertz, then it's 10 lambda in that case, or something else. And that means the directivity is very high because the aperture here is much larger in wavelengths. And it's a typical thing that's happens in these kind of horn antennas. So also in these ones here, that the higher you go in frequency, the higher directivity. So your beam get more and more narrow when you go up in frequency. And to understand this type of antennas, the simplest thing of doing is actually to look at the aperture. So what is the physical aperture on these ones? And then you use that they have some typical aperture efficiency. So it's like some rule of thumbs. And for a well-designed antenna, which of course you don't really know when you see the horn if it is good or not, but if it is well designed, it has an aperture efficiency in the range of like 0.5, 0.6, maybe 0.7 to 0.8. So something in that range. And that means that it's using these aperture here very efficiently. And that means that you can then relate the physical aperture to the effective area of these ones, because you have the aperture efficiency. And that is just a quotient between those two. And that could then say what is approximately the gain of this antenna, because the gain is then related here to the effective area, which then will be related to the physical area here in wavelengths. So that means that we can get a fair idea of the performance of this antenna just from its size and knowing what type of aperture efficiency we have. Of course, the more accurate it is, the more we know. But for many cases, it can be sufficient to have this rule of thumb, 0.5 to 0.8. So take some value there. You get some approximation of what the gain is. And if you want more details, of course, you can look at the product spec of it and so on. You can understand it better. But as a rule of thumb, you can use very, very simple formulas for it. And as I mentioned then, that the gain here increases with the frequency because, of course, the lambda here gets shorter. So the area is always the same, the physical area, and lambda gets shorter, which means gain goes up. And that will happen over the range of operation of this kind of horn antenna. So if we then look at some horn antennas and we can see what they look like, I will just probably show you one or two here, and then we'll go into the parabolic reflector. This is a very old one, but it got very famous. And you can see the structure of it here. It looks very odd. This is a more modern photo of it. And in this case, it's some 15 meter long and an aperture of 6 times 6 meters. So the radiation goes out through this aperture here. So it's in some ways a horn that is really fed inside here, and then it has some shape here, and then it radiates out of that one. And it's some combination of horn and parabolic reflector type in these cases. The gain of this one was approximately 43 dBi, aperture efficiency of around 76%. And this one got famous because actually they received the Nobel Prize. And you know that that is handed out now in 3 days, but online this year in the Nobel Prizes. And this was the discovery of the microwave background radiation, which essentially is this from the Big Bang, you know, the start of the expansion of the universe that comes at, I think, at 3 degree Kelvin radiation towards us that actually can be discovered. And it was discovered by measurements, and they thought it was a measurement error first when they looked at the radiation from sky from this kind of microscopes. But it wasn't. They thought it was birds, or they thought anything from the beginning, but it actually was correlated to this background radiation of the microwaves. And for this, they received the Nobel Prize 1978, so quite a few years ago. Slot antennas, a different type of antenna we will not talk a lot about. We talked about self-complementary antennas before, and this is not a self-complementary antenna, but it is a complementary antenna that if you know your dipole And then you make a slot where you then do the opposite. So you think you do your dipole, but you remove metal instead of adding the metal that radiates. Then you have a very simple relationship between them. And that is that the impedance of your dipole multiplied by the impedance of the slot is the same thing as we had in the self-complementary one, the free space impedance squared over 4. That means that if you know your dipole, you know your slot antenna fairly well. So we can actually get it out in that case. So if you had your dipole here at 73 ohms, it means that your slot half wavelength dipole will in that case be around 500 ohms. And that is in some ways how we can make a slot antenna. And then of course you can modify that to work better. But that's one type of this aperture antennas. We will not look much into it. Because now we will have to go into the big piece of this, which are the reflector antennas. And the reflector antenna is what you're going to build to the lab. So some directive antenna types that we've been looking at, and this will now be the super one, which is really big. We've seen that we can build arrays to get a high directivity. You know, putting elements similar next to each other, we make a large aperture, we increase the directivity. We looked at the Yagi-Uda antenna, which was an end-fire type array. So that was a high directivity antenna. And corner reflector we mentioned. Now I will go through the corner reflector and talk about it as its properties. And then we have the parabolic type antennas. And those are the ones that's used for really high directivity, where you can get the radiation from, what you say, some feed that sits here, and you can get a very large aperture out of that one. So it can translate the size of the feed to something which a large aperture. A large aperture means high directivity for these cases. So typical reflector antennas are these parabolic antennas, and typically a center-fed reflector antenna would then have a feed here. It shoots up rays here, and then the rays goes straight out here. So they radiate and then Snell's law with the same angle in and out in these cases. And then you get from a feed in the center, you get this radiation. A bad part with this is, of course, you need to mechanically put your feed there. And that means that the radiation might hit this feed. So a very common version to remove the structure of this and still use a parabolic one is to do only a piece of this. So here you put the feed and you actually radiate only a small part of this parabolic reflector. So it can come out here and then it doesn't really hit these metallic pieces that supports the feed. That's an off-center version in some ways. A Cassegrain is another version, which is also very popular from optics and building, what to say, magnification telescopes and so on. Then you put a feed inside here and you have a sub-reflector here and then you have a main reflector here. So you do this enhancement 2 times in some ways. That's a Cassegrain type configuration. So there are many types of this. What is common for all of these cases is that the diameter here has to be much, much larger than the wavelengths. So the structure that we have here, this structure here is much, much larger than the wavelengths. And when I talk about much larger, I mean, the minimum you could think about is like a factor of 5 or something. But it's no problem to go up to a factor of 1,000, 10,000, 100,000. So it can be large, really large in terms of wavelengths. There's no limitation there. Another case that's happened here is that the feed distance is also much larger than the wavelengths. So that is the distance that sits here. The distance from your reflector to your feed, that is also many wavelengths in size. So everything here is many wavelengths, which means it's large structures. And the way to analyze this is typically with rays. So even the pictures I've been drawing here are rays. And they are sometimes called geometrical optics. And then there are modifications of that we called GTD, geometrical theory of diffraction, physical optics. And then it can also be used nowadays, for example, like what you have in FECO, which is this method of moments and acceleration techniques. But thinking about them, it is really the ray picture that dominates. That comes into reflector antennas. And we will look at parabolic reflectors in this course. So this is a typical parabolic reflector. So the parabolic reflector is defined by this equation. So rho is the distance in the xy plane. So rho squared is x squared plus y squared. And then that is related to the distance in z here, what you can see there. So z is the coordinate in this direction, and of course y is in this direction and x is in this direction. So that means you get some shape that comes out here. And this is this second order equation that comes in. So the parabolic equation that comes in there. And that is then used because it has some unique features that are really, really good. And that's why it's used a lot in optics, and it's used a lot for antennas and reflectors. So it has a focal point. That is the key part of this one. So if you think about it as a receiving system, then what that means is that you have rays coming in here, it bounces here, and then it hits this focal point. Another ray that hits here, it bounced here, it hits the focal point. And they add up in phase too. So if you would take in, for example, this and you illuminate it with some incident field, you get very, very high intensity in that focal point. And the opposite, if I now radiate from the focal point, I will get an aperture here which has a constant phase, and then basically radiate straight up here. And now I can get a very large aperture, many wavelengths in size. So very, very high directivity that comes out. And yeah, so the distance will then be the same for all of these reflected fields. So if I take it from different points, it's always the same distance to a specific focal point that sits there. So I get this aperture plane here. It has some diameter, which is the same as the diameter of my parabolic reflector, and it has a uniform phase over it. And that means that that is what radiates in some ways. So propagating from this one, the ray can take like this path, and then I add up that one. If it takes this one, it goes down and it goes up there. And if I add those two, or not add, if I compare those two lengths, so down and up, I add those two, it's always the same wherever it hits this parabolic reflector. And that means that I get this phase on these ones to be uniform, the same phase everywhere. And if I want to see that, of course, I can calculate it. So if I look here at my radiation, I have a coordinate system. I put Z0 at this point. So here Z is equal to minus F. That's where I hit the parabolic reflector. And then I put this distance rho in the X and Y direction. And then I can sum up what is the length of this one plus the length of this one. What is those two if I add it up here? And that I can then show that this is independent of the position where this one sits in some ways. So if I take my equations here, I have my parabolic reflector, and then I can just simplify that parabolic reflector of saying what is the Z coordinate as a function of rho in these cases. And I use geometrical optics to analyze it. And the distance of these ones, if you think what the distance should be, then you can start down there. The distance, this is F, and then you go up again. So two-way, then it's 2F. So that is the distance I go if I go straight down and straight up. And if I go another one, then I can go this part plus this part. That is then I have to add here what is R squared in these cases. And I can write it up by adding the two other pieces that sits there. So adding this distance and this distance squared, and then plugging in what the equation is on these ones. So I have what the equation is up here from the F. And if I do that, I can show this is equal to Z plus 2F. And that means that R is the same thing as I had up here. And that means it's the same distance. That's a very, very quick derivation. You will do it in the exercise yourself. So that is one of the properties that we have. And that means that what we get out of this parabolic reflector is really some almost uniform field distribution over a large circular aperture. And then we take the Fourier transform of this and we get the far field. And this can now be a very, very large aperture that sits there. So if you look at the radiation from a circular aperture, because typical reflectors have a circular aperture, we have to do the same thing here, that we determine the radiation vectors from it. And we do it now from an assumed electric field. So we have a magnetic radiation vector. And now I have to integrate this over this circular aperture. This is a little bit more complicated than the rectangular aperture that you had before, where you had this sinc function, but we can do the same thing here. So if we compute this once, yes, we can integrate this function. Now I integrate it over phi and rho. So I put in some angles here. So I have some phi angle that comes here, and I have some distance out here that is rho. So I can integrate from 0 to 2 pi, and then from 0 to a over these coordinates. And if I do that, I will get what's called Bessel functions. So these integrals are defining the Bessel functions, and the solution you can get out of it is very similar to this sinc function. But instead of that cases where you had a sign there, you have a Bessel function. That is what sits there. So almost the sinc function, but in Bessel functions instead. And then they have the same properties you had in the rectangular one. So only some details. You have some side lobes that basically comes here. So you will get some side lobe levels that decays the further out you go. But otherwise, very, very similar type. And of course, that means that if you don't want these high side lobes, what you do is that your aperture will have a high intensity in here. And then when you go to the graduation edge of it, you lower the intensity of the radiation to that part. So you taper the illumination. And if you do that, you push down these side lobes. But it means that your aperture is slightly smaller, effectively. So the beam gets a little bit larger. That is the effect that comes in. So if we look at some typical reflectors of things, this is, for example, the VLA I showed you before. So this is in New Mexico in the US. You might have seen it in some movies. It exists a little bit everywhere. And I think I showed you some pictures of it before. It sits somewhere there in the US. And if we just take this structure, it has a diameter here of 25 meters, and it has wavelengths here between 90 centimeters and 7 millimeters. So it means that the aperture here in wavelengths is between 28 and 3,570, basically. So very, very many wavelengths in structure. And that's why they can get this very narrow beam. And of course, then you can add up in some ways the array factor to this, and you can really see good resolution of the sky. If you go to another one, which actually got very famous just this last week, you might have seen it in the media. Of course, you might have seen it in movies before. That is the Arecibo Observatory. And unfortunately now we have to end the date of this one. It actually collapsed this year. You can see some movies on it. You can see some links here. And this used to be the largest dish antenna in the world. And that was until it was actually built one in China just a few years ago. I will show you that on the next slide. So 2016, it came a new one. And the size of this one is 305 meters. So that is what you have here. So you can see the dish there, enormous in size in some ways. The gain of this one is approximately 10 to the power of 7, so 70 dBi. And of course, now 70 dBi doesn't sound so much, more like 20 in some ways. But think about it, instead of the directivity or gain of your patch antenna, maybe 3, 4 to 10 in some ways, it's just 10 to the power of 7. It's an enormous number of gain of these ones. And this was at the frequency here around 2 gigahertz in some ways. So very, very, very high. Of course, if you use the entire structure, so if you think it has some effective area here, you would actually get 10 to the power of 11. But that is not used because this is not a parabolic reflector. This is actually a circular reflector. And now you can ask him, why don't you make a parabolic reflector when I say the parabolic reflector is so good? The problem with the parabolic reflector is that it has one focal point. And if you radiate from that one, you get the direction out. Then you can ask the question, how would I tilt the radiation in different dimensions or directions? Then you have to move your parabolic reflector. Okay, how do you move your parabolic reflector? It's 305 meters, it's standing on ground. I mean, you cannot tilt it. The only thing you can do is to let Earth rotate. And when you let Earth rotate, you basically get an array. So synthetically, you get an array of these ones. So you can add up pictures from different rotation angles. But then you don't want only cut in one dimension. You want to be able to look in other directions too, which is against the rotation. And what you do here is that you move your feed. So in the structure here, you can actually move the feed place here. And when you move the feed, you only illuminate like one piece of these ones. And this circular, spherical reflector then is approximately parabolic over that structure. And then you're reducing only a part of this radiation, but it gives flexibility to direct it. And that is the reason between these two differences. So you don't use it as a parabolic reflector. And in movies, yeah, many people have been in movies of this one. I think the most famous is James Bond, who fall down there. But then, as I mentioned, now this one fall down instead. So this one just happened this fall, and actually last week it collapsed again. So you might have seen it in the media just this week. And nowadays it looks like this. You can find many pictures of it on the internet, and you can find movies where this actually is collapsing. And what's happening is that they were decommissioning it because it was getting old and so on, but they were first having plans to actually do things with it. But then actually these ones even fall down on top of it. And you can see it's completely crashed once it's done. So unfortunately, that one is gone. But on the other hand, we got a new one. So this FAST, which is the 500-meter aperture spherical radio telescope, is in China instead. So it's even larger in these cases. So this is 500 meters in diameter, and it's operating here from 70 megahertz to 3 gigahertz. Typical frequencies you have in the lower communication. It has the first observation and operational in 2016, discoveries in 2017, and it's been fully operational now since January 2020. So that's also maybe connected to that Arecibo is not, was used anymore, because actually it came something that was even bigger. And you can see the size of it over here. Enormous in size, 500 meters in size. And again, you can see it has the same structure here where you can feed and you can move the feed. And then of course Earth rotates. And then you only use a fraction of this part, but it's still a huge area that you use for this. So very, very large arrays that you can get. This is a version in Sweden. This is the IceCat, sits up in northern Sweden. And what you do with that is actually to study very nice stuff, for example, part of the northern lights and so on. So you try to study the ionosphere, the magnetosphere that sits above us in some ways. And that is partly responsible for this northern lights that we can see. We are a little bit lack of time, so I will not show much more of that. There's another version for these radio telescopes. This is typical TV antennas. And of course, they exist in many different versions. A typical version here is around 10 gigahertz, which is the wavelength of 3 centimeters. And yeah, here you can see some. This is in Aruba, Caribbean. This is up in Norway. And of course, you can see they are directed in totally different directions. And the reason for this is, of course, one of them is close to the equator and one is very close to the North Pole. And when you actually sit this far north, as you do up in northern Sweden and Norway, actually your satellites are basically around the horizon. They are not straight up for you anymore. So you actually do direct your dishes fairly along the horizon, pretty close to the horizon. This is a hat antenna. This is what sits in many base stations as this point-to-point radiation. It has very good aperture efficiency. So it's a specific feed structures. So doing a reflector antenna, of course, one part is to designing a reflector, but in some ways it's fairly simple because it's a parabolic reflector. The hard part is usually to do this feed that sits there. This is called a hat feed on that one. It's usually used in many of the microwave links between base stations. This is a wire reflector. So of course, for a circular polarization, if you have them outside, wind is a big problem. And if the wind is there, you can just put the metallic net instead. And that can figure out where your polarization is. And that means that the polarization is along these wires. Otherwise, it will go straight through this net. And you can even figure out basically what the frequency range is, because it has to do with this net that sits there. And we have to go into your corner reflectors. I will jump that too. Compact ranges, we talked in the measurements, so let's skip that one too. So another type of this reflector or high gain antenna. So you're going to build a reflector antenna to the lab. So of course, parabolic reflector is very good. Another one that's very good is the corner reflector. And the corner reflector, we quickly looked at it once before, so now we will come back to that one. And that is instead analyzed with array factors. So the corner reflector is actually that you put a piece of metal here. Here, you can see it. So you basically put out some V shape of metals. So metal on one side, metal on one side. And then you put your feed between those two. So that is in some ways a dipole here, could be a monopole that sits there, something that then radiates, and it radiates in both directions around here. To analyze these ones, we then use image theory. So if we take our corner reflector, we have one wall of metal here, we have one wall here, and that means that we get one reflection point there, one reflection point here, but also one reflection point behind it. So this one will radiate as from these 4 point sources. That's it. And from those, we can determine the array factor. So we can sum up the contributions from all of them. And the result that we get out here is in some way some array factor, which is this 2 cosine. KD is the distance. That's it. And if we take these ones, we can then see what the radiation pattern is. So if I add the Hertzian dipole inside of them, we assume that we can get the radiation intensity, normalized patterns in these cases. And we can actually see what we get out here in radiation patterns for these cases. And these are now for, 3 different distances. So in some ways here, lambda, quarter of a wavelength, half a wavelength, and 1 wavelength. The red curve that sits there is equal to the lambda for these cases. So what you can see is that if you distance to the center of these ones, so again, the distance is from the corner there to your feed. If that distance in these cases is now around half a wavelength or below, even quarter of a wavelength, you get this blue and green pattern that sits there. If it starts to go up to 1 wavelength, it breaks off. So that says that your design rule is, around half a wavelength is good. And you get a fairly nice radiation pattern out. And this is then the radiation pattern that you can typically get from this corner reflector. It has a directivity around 11 for a feed distance of lambda. So this is a very, very simple version to build in some ways, to build a reflector antenna. If you would compare it, because of course you are now going to build one for the lab that you do this week. So if you choose to do a parabolic reflector, which is, option 1, what you should think about there is that you would like to have a directive feed. You need a distance between, or a size of your reflector. So a diameter of that one, which is many wavelengths. And also you need a distance to the feed that is many wavelengths. And the feed here is in the focal point of your parabolic reflector. So the shape of your parabolic reflector determines the focal point. And that should be many wavelengths. And it's independent of the wavelengths. If you instead do a corner reflector, so if you do this one, then you should have some omnidirectional feed, typically dipole, because it should radiate in both directions. The size of your reflector in these cases, so the size of these ones, has to be a few wavelengths, like 3, 4 wavelengths or something, 5 on that size. And the feed distance for constructive interference should be in this range. So between quarter of a wavelength and half a wavelength. And that is then the distance here to your feed point. So that's the basic design rules for these ones. And what you are going to do is you pick one reflector antenna you would like to build. Find some material you can build it with. And typical aluminium foil is really good. So like the way you cook at home, you cannot use plastic foil, it doesn't reflect, but aluminium foil. And you can cover some paper with that one, and you can mechanically build a structure that actually is this reflector. So if you do a corner reflector, of course, you need one side here, you need one side here, you need some mechanical support that means this needs to be put together, and you need something to attach your antenna to it in the feed point. And that you can build from paper. And a typical good version of doing it is to use something like this. Typical tray of paper here, some cardboard paper you can get out, and you can actually shape something from this. And if you bend it, you can do something that is like a parabolic reflector. Maybe not a Cassegrain, but you can shape it around it. And it's completely up to you what you build. So try to have some fun, try to figure out what is a good design, and then you bring that with you. So you build it at home, you bring it with you to the lab, and you will actually measure it, and we'll see who gets the best reflector antenna. So we will, out of time, we skip the lens antennas. We will not go through those. There are some details about that. And that means that now we're into, the second last week of the course. We will have an exercise on Wednesday. And then on Thursday, we will actually start talking about generally small antennas. So one thing that's been very, very common and will continue to be very common to the years to come is that we shrink the antennas. What's happened a lot in the last couple of 10, 15, 20 years is that you need to make antennas that is sub-wavelengths in size, which means they are electrically small. Now what's happening is that we go up actually to what's called small physically antennas. So we go up to 60 gigahertz, 100 gigahertz. They are not physically small, they are small in a different way. And we will look on this lecture on Thursday, what does this miniaturization of antenna means? Because it's there and it will continue to be with us for many years to come, especially these electrically small antennas. When you shrink your antennas below your half a wavelengths, what is the price we have to pay for that? The third labs are also this week, and I think all of you have already signed up for it. If you have not done it, check that you are really signed up for the lab. And for the lab, of course, you have your patch antennas you will measure, the one that you have built, and you should also build your reflector antenna. That's what you're going to do. And also the quiz, I know one is soon closing and the next one is opening on Thursday. I hope you have done all the quizzes. So with that, I will stop the recording, and maybe there are